Alright, so now that you already have the idea, so how do we check for linear dependency between two functions? So next, I'm going to give you the idea before I start with the whole calculation. So I'm going to give you the idea how to find the yp, which is the particular integral. Remember, when we write down the solution, there will be two component, which is going to be yc and yp. So now, based on the function f of x or f of t or f of whatever variable that is, you have to come out with the particular integral. So how do you come out with the particular integral? Okay, so the particular integral is going to depend on the function f of x that you had on the right hand side of the equation. Remember, so equation is going to be on the form of a y double prime plus by prime plus cy equal the function f of x, and your function yp is going to depend on the function f of x on the right hand side. Okay, but let me warn you the thing about undetermined coefficient. So for the case of undetermined coefficient, so we have two methods of solving non-homogeneous, UC and also VOP. So what is the difference between both of them? VOP is a very powerful method, no matter what is going to be the function f of x. So you can always solve that by using VOP, but it's going to be quite complicated because of the method itself. Okay, however, for the case of undetermined coefficient, it's going to be easier. But when the method is easy, there will be restrictions. So what is the restrictions? You can only use undetermined coefficient. So when your function f of x is false in any of these categories right here, basically it's a combination of three functions. So you can only use undetermined coefficient when your function f of x is a polynomial. For example, you have x squared, 3x squared, anything x raised to the power is positive. So that is going to be called as being polynomial. Or if your function f of x is in terms of exponential x, exponential negative x, and so on, in terms of exponential. And the third one is going to be in terms of sine and cos. What if you have 1 over sine, 1 over cos? The answer is no. It is only restricted to sine and cos only. Other than that, you cannot use undetermined coefficient, so you have to use VOP. Okay, and you can also use undetermined coefficient when you have linear combination of these cases. What is linear combination? So your function is combined together with plus or minus, so that is called as a linear combination. For example, if I have x is a polynomial, this is a sine or cosine. For example, you have x plus sine x or x minus sine x, so that is called as linear combination. Or if you have products of any of these three right here, so it could either be polynomial multiplied by exponential, or exponential multiplied by sine, or polynomial multiplied by cos, and so on. So as long as it involves three type of function right here, polynomial, exponential, sine, and cosine, so you can use undetermined coefficient. But other than that, for example, if you have a function that is going to be in terms of tangent or something like that, that is not among what we have listed over here, okay, automatically it is not possible to use undetermined coefficient. For example, if I have an equation that looks like this, plus y prime plus y equal 1 over x. So is this polynomial? No, remember, because this is x to the power of -1. Polynomial is only concerned when x is raised to the power of a positive. When it's negative, it's not a polynomial, it's called as a rational function. And for cases like this, can you use UC? The answer is no. Okay, it's not among what listed over here. You can only use this for polynomial, exponential, sine, and cosine. Other than that, it's a big no. Okay, where's my eraser here? Okay, so let me give you the idea now. So how do we find for yp? So let's suppose you are given an equation that looks like this. So you have y double prime plus y prime plus 2y equal x squared plus 3x plus 1. So here this is not equal 0. We know that this is going to be a non-homogeneous equation. So how do we find the yp? So first of all, I'm going to write the fact that our function f of x, so that is going to be given by x squared plus 3x plus 1. So what I'm going to do is I'm going to draw a curly bracket. So that is going to be my curly bracket, okay? And how do I determine what is going to be the element in the curly bracket? Okay, so the first element in the curly bracket is going to be the highest, for the case of polynomial, is going to be the highest power of the variable. So here, what happened is that I have here x to the power of 0, x to the power of 1, x to the power of 2. Of course, x to the power of 2 is going to be the highest. Let me put a constant over here to prove a point. So let's say here I have 5. And this is 5x squared. So even when you have 5x squared, remember, you don't need the constant, you remove the constant, you only take the variable. So therefore, for this case, so the first element in my family of derivative is going to be x squared. So you pick the highest power of x in there, or if you're using t, the highest power of t, and so on. Okay, what is going to be the preceding element? Preceding element meaning the next element. Okay, but before that, let me tell you, so the fact that this element in the curly bracket over here, so this is being called as the family of derivatives. And of course, how do you get derivatives? So the only way of getting derivatives is by differentiating. So that is why what happened is that when I differentiate x squared, so I will get 2x. And again, when I remove the constant 2, I simply will end up with x. So that will be my next element. So if I wanted to find the preceding element, I'm going to differentiate x. And I know that when I differentiate x, I will end up with 1. Okay, and when I differentiate with 1, and I know that I'm going to end up with 0. So I'm going to stop right there. So therefore, so my element in my family of derivative for this case is going to be x squared, x to the power of 1, and also x to the power of 0, which is going to be 1. Okay, so the next thing that we're going to do is we're going to create a linear combination of this. So how do I create linear combination? All I have to do is for each of this element in my family of derivative, so I'm going to multiply that by a constant. Okay, for example, for x squared, I'm going to multiply this by constant c, this one by constant d, this one by a constant e, and all I have to do is add them up together. So that will be called as a linear combination, meaning that for this case, my ypx, so the first element is going to be c multiplied by x squared, that is cx squared, plus d multiplied by x, that will be a dx, and e multiplied by 1, that is going to be e. So that is going to be the particular integral for this first example. If I have a function of 5x squared plus 3x plus 1 as the f of x function. Okay, let me demonstrate this by using another example. So let's suppose now your function, I'm not using x anymore, I'm using t. Let's say a function f of t is given by t cubed plus 1. So the idea is still going to be the same. What I'm going to do is I'm going to write down the family of derivative. Okay, and remember, and the first element of the family of derivative will be the highest power of the variable in there. So therefore, for this case, there is no doubt that t cubed is going to be the highest in there. So therefore, so I'm going to write that, let me put a constant again, just to make sure that you understand this. For example, I have 2t cubed plus 1. Again, I'm going to remove the constant. I don't need the constant. I simply going to put in here t to the power of 3. So that is going to be the highest power of the variable in there. And when I differentiate t cubed, I'll end up with 3t to the power of 2. But then again, I don't need the constant 3. I simply need the variable. So for this case is going to be t squared. That will be my second element. And again, when I differentiate t squared, I will get a 2t. But I don't need the 2. I simply need the t. So therefore, the third element will be t. And when I differentiate t, I will get 1. And that will be the end of the element. Because I know that when I differentiate 1, that will be a 0. So we don't need that in here. And after that, all I have to do is I'm going to multiply this by constants. I'm going to multiply this by c, d, e, and also f. And now that we have all those components, so we can write that for this case, my yp of t, because t is my independent variable, is going to be given by c multiplied by t cubed plus d multiplied by t squared plus e multiplied by t plus a function of f. Actually, when you make linear combination, it doesn't matter if you put plus or minus. But for the sake of our calculation, it's going to be the easiest if you use plus instead of a minus. So that is why we always add them up. Okay, remember it's always a plus in between. Okay, so that is going to be the yp for the second example. So this is going to be for the case of polynomial. So you take the variable with the highest power. Right, for the second case, which you could also come across function of exponential. So how do you deal with that? So the idea is still going to be the same. All you have to do is you remove the constant. So therefore, my first element in the family of derivative is going to be exponential of 2x. And what happened is that when I differentiate exponential of 2x, I know that I will end up with 2 exponential of 2x. But notice what happened is that when I remove the 2, I'll end up with a function that is exactly the same as what written in there. So that is why when you have the case of exponential, there is only going to be one element in the family of derivative, which is going to be the exponential by itself. Why? Because exponential, when you differentiate that repeatedly, only the constant goes to the front, but the power of an exponential, it doesn't change. It's still going to remain as the same exponential over and over again. So that is why, for the case of exponential, there is only going to be one element in there. You multiply this, for example, by constant d. So therefore, I can write right away the fact that my yp of x is going to equal d exponential of 2x. So that is going to be the yp. Okay, remember, When you have polynomial, start with the highest power until 1. And when you have exponential, there's only going to be one element, so which is going to be the exponential by itself. So now let's have a look at the third case for which you have sine or cosine. Okay, the idea is still going to be the same. What I'm going to do is I'm going to remove the constant and I'm going to write down the family of derivative. My first element is going to be cos of x, and when I differentiate cos of x, I will get negative sine of x. But the thing is that negative is actually constant. It's actually negative of 1, so I don't need it. So therefore, the second element is going to be sine of x. And the thing is that when I differentiate sine of x, I know that I'm going to get another cos of x, which I already have right here. So that is why for the case of sine and cos, what happened is that every single time you write down the family of derivative, there will be only two elements of them in there. They come in pair. When there is cos, there will be sine as well, because when you differentiate cos and sine, it's going to be cos and sine, positive, negative repeatedly. But remember, the positive, negative is just a constant. When you remove, basically it's just going to be the same function. What do I mean by that? Because of this. Sine, cos, negative sine, negative cos. And of course, when I remove the negative, basically they are just the same function being repeated. So that is why when you have sine and cosine, so there is only going to be two elements in the family of derivative. Okay, so that is why for this case, I'm going to write the particular integral, my yp of x. So if I were to multiply this by c and d, so I'll end up with c cos of x plus d sine of x. Okay, so that will be the yp when I have cosine or sine function. Okay, so it will be the same for this one as well. So here what happened is that if I were to refer to the sine of 2x and I remove the constant 2, I know that I'm going to end up with two elements, which is going to be sine 2x and also cos of 2x. Remember, they come in pair. There will be sine and one is going to be cos. However, do I still need to write for this one? No, because I know that this one is also going to create the same. So which is going to be cos 2x and also sine 2x. So we already have the same element in there. So that is why we don't need to have them twice. We only need to write them once. So therefore, for this case, my family of derivative is simply going to be given by sine 2x and also cos 2x. And when I multiply this by a variable of c and d, so I can write the fact that my yp of x is going to be given by c sine of 2x plus d cos of 2x. So that is going to be my particular integral for this particular case. Okay. Right, so I would like to repeat that again. So the fact that when you have polynomials, start with the highest power of the polynomial until you get a value of 1. Okay, so that will be how many elements you can have is going to depend on highest power. Okay, when you have exponential, there is only going to be one element in the family of derivative, which is going to be the exponential by itself. And when you have the case of sine and cos, there are going to be two elements in the family of derivative. They come in pair. Whenever there is cos, there will be cos and sine. And whenever there is sine, there will be sine and cos as well. So which one comes first doesn't matter, as long as you have both sine and also cos in the particular integral. Okay, so that will be the idea. Alright, so now I'm going to start with this particular example right here. I'm going to start showing you how do we solve for undetermined coefficient. So there will be multiple cases, and I'm going to be showing you about like 5 or, no, it's not going to be 5, but 6 to 7 examples. Okay, but however, the examples, the method, the steps are going to be exactly the same. Only the cases are going to vary. Like for example, example 1 and example 2, I'll be showing you the case of polynomial. 3 will be an exponential with example number 4, and then example 5 will be case of sine and cosine and so on. Okay. However, the step is going to be the same. Whenever you understand one example, you should have no problem dealing with the other ones as well. So I'm going to start with the first one. Here I'm going to be solving this equation right here. So y double prime minus 2y prime plus y equal to x squared minus 1. So this is going to be our function f of x. And of course, there are two types of solution, general and particular. And because this is my first example, I'm going to show you the case of particular solution so that you are able to differentiate between them. So let's start with the first one. Remember, I did mention to you for the case of undetermined coefficient, our solution is going to be given by yx is equal yc plus yp. There are two components. So I'm going to start with the first component, which is going to be the yc. How do we find the yc? So remember, YC is a homogeneous equation. So YC stands for homogeneous solution. So you can only get homogeneous solution if your equation is homogeneous. However, this equation over here, it is not equal 0. It is not homogeneous. So how do I make it homogeneous? Simple. So it's going to be homogeneous if this over here is equal 0. So that is what I'm going to do. Okay, so I'm going to make it equal 0. So my function is going to be y double prime minus 2y prime plus y, and that is going to equal 0. All I did is I set the right hand side equal 0. Instead of 2x minus 1, so 2x squared minus 1, so I put this as equal 0. Now it's going to be a homogeneous equation, then only I can get a homogeneous solution. But the left hand side is exactly the same. So these three terms and these three terms, they are the same thing. I only change the right hand side of the equation. I put it as equal 0. And of course, we're going to change this to characteristic equation. So this is the same as what we have done in 2.1, previous subtopic. So I'll end up with m squared minus 2m plus 1 equals 0. So based on your roots, you could either get distinct solution, equal solution, or the complex root solution. Okay, and for this case, I know that when I factorize this, I'll end up with m minus 1 squared equals 0. So this is going to be the case of distinct roots, for which what happened is that my m1 is going to equal 1, and my m2 is also going to equal 1. I'm going to have equal roots. So let me put over here. So I'm going to have the case of equal roots. So that is why when I write down my solution, so what is my variable? So it's going to be x. So according to what we have discussed before, our solution when we have equal roots, yc of x is going to equal a plus bx exponential of 1x. So my m is equal 1, so it's going to be exponential of 1x. So that is simply going to be exponential of x. Okay, so now that I am done with the yc, so that's it. So yc is just 2 marks. So all you have to do is, so change it to homogeneous equation, find the roots, write down the solution, and then you are good to go with the yp. So now we're going to find the second component. So that is going to be the yp. And of course, as we have seen before, so yp is going to depend on the f of x. And for this case, my function f of x on the right hand side of the equation is given by 2x squared minus 1. So now let's write down the family of derivative. For this case, the highest power is going to be x squared. Remember, we don't need the 2. When I differentiate x squared, I will get 2x. Remove the 2, I will get x. And the last element will be 1. And then all I have to do is multiply this by constant c, d, and e. So if you notice, I don't use a and b when I multiply that by constant and make a linear combination. The reason is that a and b is going to come from here. It's going to be from the yc. So that is why for the yp, choose c until z. Any of those, as long as it's not a and b. So therefore now I can write that. So for this case, my yp of x, so that will be given by c x squared plus dx plus e. So that is going to be, basically this is already our solution. So our solution is going to be yp is going to be cx squared plus dx plus e. Okay, however, remember, so make it a habit, every single time that you have written your yp, so you have to fulfill the condition. Remember the condition? So the condition is that yc and yp, so they must be linearly independent. Remember, what does it mean by being linearly independent? So they must not be the same. The idea is going to be as what I have discussed in the previous video. So now, remember I told you before we start removing the constant, if you have come across something like this, expand it first. So this is going to be a exponential of x plus bx exponential of x. So now I'm going to start comparing all the elements. So here I'm going to have exponential x, x exponential x. Remember, only remove a, b, c, d, and e, or whatever that is. So this is going to be x squared, this is going to be x, and this is actually e multiplied by 1. It's not e by itself, it's actually e multiplied by 1. When I compare all of them, this is exponential x, x exponential x, x squared, x, and 1. None of them are the same. So automatically they are linearly independent. So yes, I can use this as my yp. If they are linearly dependent, no, that is not going to be your yp. You have to come out with something else. That I will explain in the next example. But for now, for this case, so after you check, you verified that these two, they are linearly independent. Then only you can proceed to your next calculation. Alright, so basically this is already our solution, but there's going to be another drawback. The fact that you have to figure out what is the exact value of C, D, and E. And how do we find the value of C, D, and E? So we are going to use back the original equation, and I'm referring to this equation right here. So what happened is that you're going to substitute y, y prime, and y double prime. Okay, and then by using that equation, you're going to find what is going to be C, D, and E. So here what we have is yp. So yp is going to go here. So you have to find y prime and also y double prime. So you have to differentiate your yp twice. So now I'm going to start differentiating. Okay, so this is my y. Now I'm going to find the y prime. So y prime, when I differentiate this, I'll get 2cx plus d. And I also need the second derivative, y double prime, which for this case is going to be given by 2c. And I'm going to start substituting into the original equation. So my original equation is y double prime minus 2y prime plus y, and that is equal to x squared minus 1. This is the original equation in the question. Differential equation from question. Okay, so we don't change anything, we just simply copy it down. And now I'm going to substitute according to what we have find up there. We're going to substitute the y double prime, y prime, and also y. So I'm going to start by substituting the y double prime. Okay, for this case, so let me put a red bracket around, and I need a black as well. Okay, so y double prime, according to what we have over here, is going to be given by 2c. That is my y double prime. And then I'm going to have a minus 2. And then I'm going to substitute the y prime, so which is given by 2cx plus d. And then I'm going to have plus y. And my y, according to the what we have up here, so that is going to be given by cx squared plus dx plus e. And that is going to equal... there goes my red bracket, and that is going to equal 2x squared minus 1. So what happened is that when I have this equation, I'm going to compare the left hand side and also the right hand side. The idea is going to be something like this. For example, if I have a cx squared equal to x, so straight away we can tell that the value of c, that is going to equal 2. So this is what we're doing over here. So we're going to be comparing. Okay, so now before I start comparing, let me simplify the equation first. I'm going to rearrange them according to the starting with the highest power. So we start with this term right here. So the highest power is going to be cx squared. Okay, let me expand them all first. So for the first example, I'm going to show it to you in detail. So when I expand this, I'll get a 2c, so minus 4cx. Do not miss out the constant, the 2 outside. And then I'm going to have a minus 2d, and here I'm going to have plus cx squared plus dx plus e, and that is going to equal 2x squared minus 1. And the next step I'm going to do is I'm going to rearrange them. So I'm going to start with the highest power until the lowest power, which is going to be the constants. So I'm going to start with the highest power, which is going to be cx squared. So this is going to be the term, and then I'm going to put together all the term with the x. Okay, I'm going to factor them, so which is going to be this and that, for which I'll get negative 4c plus d. Okay, so that is going to be the term that are related to x to the power of 1. And then I'm going to collect all the terms that are constants. So these terms, they don't have variable, so they are actually constants, and they're going to be given by 2c minus 2d plus e, and that is going to equal 2x squared minus 1. So let me add another page. Okay, so now I'm going to start comparing like what I've said to you just now. I'm going to start with the highest power, which is going to be x to the power of 2. Okay, now let's compare the coefficient. For x to the power of 2, on the left hand side, I have cx squared is equal 2x squared. So from here, when we compare, so I end up with cx squared is equal 2x squared. So straight away we can tell what is going to be the c value. The c value is going to equal 2. So I obtain the first constant, which is going to be c. And then I'm going to start comparing for x to the power of 1. Okay, on this side, for x to the power of 1, this is going to be the coefficient. So this is what the constant that is being multiplied by x. And on this side, what happened is that, do I have any constant multiplied by x? No. Then that is actually 0 multiplied by x. So we know that the coefficient of x on the right hand side is going to equal 0. So here we can write that. So negative 4c plus d. So that is going to equal 0. So we already know the value of c. The value of c is going to equal 2. So when we substitute, I'm going to have negative 4 multiplied by 2 plus d is going to equal 0. So what is my d value? So my d value is going to equal 8. So that is going to be upon the comparison of the coefficient. And lastly will be the constant for x to the power of 0. So basically just the constant. Okay, and on the left hand side for x to the power of 0, this is going to be the constant associated with x to the power of 0, and on the right hand side this is going to be the number, which is going to be negative 1. So therefore I can write that 2c minus 2d plus e, that is going to equal negative of 1. So please do not miss out the negative. The number is negative of 1, not positive of 1. So now I already know the value of c and d. I can actually substitute in there. So I can write that e is going to equal negative 1 minus 2c, that is negative 2 multiplied by 2. And then I'm going to have it's going to be plus when I move it to the other side, plus 2 multiplied by d, which is going to be 8. I want to simplify. What value would I get over here? I will get 16 minus 5, so that is going to equal a positive of 11. So that is going to be my e value. That's going to equal 11. So now that I already know the value of the constants, c equal 2, d equal 8, and e is going to equal 11, all I have to do is substitute back into my particular integral. So this is our second component, which is the yp. So now that I already figured out the value of c, d, and e, all I have to do is substitute back in here the value of c, d, and also e. So now I can write that my yp of x for this case. So that is going to be given by c, which is 2x squared, plus d, which is going to be 8. So I'm going to have 8x, and e, which is going to equal 11. So that is going to be the ypx. Let me put this in detail for you. So my yp is given by cx squared plus dx plus e, and when I substitute, I'll end up with 2x squared, and then I'm going to have plus 8x plus 11. So that will be the yp. All right. And remember, so for the case of undetermined coefficient, our solution is going to be yx is equal yc plus yp. So all you have to do is combine them together. So what is our yc from previously? This is our yc. So write it down. So our yc is going to be given by a plus bx exponential of x, and yp is given by 2x squared plus ax plus 11. And of course, this is going to be our solution. But this over here is going to be called as a general solution. Why is it a general solution? Because our answer is in terms of a constant a and also b. Okay. So as I promised you for this one, because it's the first example, I'm going to show you particular solution as well. But I would suggest that you take 5 for now after you have listened to this particular example. Go through back and try to understand the bits that you actually left out, and then only proceed to the particular solution. So pause the video for a bit. Then only you proceed with how do you find a particular solution. But I'm going to start, but of course you can pause. Okay, now let me see what is our initial conditions. So we have two initial conditions. That is y naught is going to equal 2. And y prime 0 is going to equal 0. Again, I would like to warn you, when you find a particular solution for the case of non-homogeneous equation using undetermined coefficient, you substitute into this equation, the yx. Do not substitute into just the yc, remember? So the particular solution only comes after the general solution. After you get the general, then only you can find particular. Okay, so that is why you only substitute after you have find the general solution. Alright, so now let's start with the first initial condition, that is y naught equal 2. I'm going to substitute into this equation. Let me write the equation. So yx is going to equal a plus bx exponential of x plus 2x squared plus 8x plus 11. Okay, so now I'm going to have to substitute all the y and all the x, x. Okay, so for this case, what is going to be my y value? My y value is going to equal 2, and my x value is going to equal 0. So I'm going to have 2 is going to equal a plus b multiplied by 0, that's a 0, exponential of 0, plus 2 multiplied by 0, which is a 0, plus 8 multiplied by 0, and plus 11. Okay, so that is my equation. So I will get 2 is going to equal, so exponential of 0, that's a 1. So I'm going to have a plus 11. And straight away here we can tell what is going to be my a value. My a value is going to equal 2 minus 11. So that is going to equal negative of 9. So that will be the first constant. And now that I'm going to find b, I have to use the second initial condition, which is this one. But remember, the initial condition is not going to be on y, but it is going to be on y prime. So that is y. So you have to differentiate it first. So now let me differentiate the y prime. Okay, remember I told you before, so when you have a product that looks like this, when there is more than one x involved, automatically you cannot differentiate that directly, you have to use product rule. And when I apply product rule, so when I differentiate the one in the bracket, a is going to be 0, bx is going to be b, I'll end up with b exponential of x plus a plus bx exponential of x. So that is what happened when I differentiate the a plus bx exponential of x. Okay, u prime v plus v prime u. And then at the back, I'm going to have 4x plus 11. And of course, when I differentiate 11, that will be a 0. Alright, so now that I have this, I can substitute using the second initial condition. So my y prime and x, they are both 0. So I will get 0 is going to equal b exponential of 0 plus a plus 0 exponential of 0 and plus 0 plus 8. And let's simplify this. And so what happened is that I will get that b plus a. So that is going to equal negative of 8. But I already know that a is going to equal negative of 9. So I will get that b is going to equal negative 8 minus a, which is going to be negative 8 minus negative of 9. So I will get 9 minus 8, that is going to equal 1. So I get that my a value is going to equal negative 9 and my b value is going to equal 1. So now that I have obtained the value of a and b, so all I have to do is substitute back into the general solution. Okay, so I can write that, therefore, my particular solution y of x is going to be given by a, which is going to be, what's my a value? Negative 9. So I'm going to have negative 9 plus bx, so that is going to be plus 1x exponential of x plus 2x squared plus 8x plus 11. Is that right, the yp? So yes, 2x squared plus 8x plus 11. My a is going to equal negative 9. My b is going to equal 1. So that is going to be the solution. Okay, and this over here, so this will be the particular solution. Okay, so that is going to be the first example. So I'll show you more examples in the next videos.